And George, you can start sharing your screen.
Yes. Can you see the first page?
Yes, it's
Okay.
full screen. Everything looks fine.
Okay.
Yes, perfect. All right. Okay. So our next speaker is George Gkountoumis from Utrecht, and he will talk to us about exact moduli spaces for n equals 2, d equals 5 freely acting orbifolds. George, feel free to start.
Yeah, thank you. Thank you very much for the introduction and the invitation to give this talk. And hi, everyone. And today I will discuss about some models that are obtained by freely acting asymmetric orbifolds of type 2 string theory. And in particular, I will focus on models that preserve 8 supercharges, this amount of SUSY I denote by n equals to 2, and these models are 5-dimensional. And also, I will argue that for these models, the moduli spaces for vector multiplets and hypermultiplets are classically exact. And this talk is based on a recent paper that we had with Chris Hall and my advisor, Stefan van Doren. Let me first give you the outline of the talk. I will start with an introduction and a motivation, and then I will briefly review freely acting orbifolds. And after this, I will explain how we can construct dual pairs of orbifolds, and this will be a strong weak duality between two freely acting orbifolds. And then I will go in some details and discuss the moduli spaces of these orbifolds, and I will end with a conclusion and some comments on current and future work. Now, as I said at the beginning, today we'll be talking about models with 8 supercharges, and one way to obtain such models, which is greatly studied in the literature, is by compactifying M theory or type 2 theory on Calabi-Yau threefolds. And these models have some common characteristics. So these are geometric compactifications, and in the massless spectrum of these models, there exists at least one hypermultiplet, which is usually referred to as the universal hyper. And also the metric on the moduli space for either the vector multiplets or the hypermultiplets receives quantum corrections. So this can be, for example, brane or Worldsheet instanton corrections. And now another way to obtain models with 8 supercharges is by using asymmetric orbifolds, and this was recently also revisited in the literature. Now, these are examples of non-geometric compactifications, and also there are examples with no hypermultiplets, with no massless hypermultiplets in the spectrum. And my aim today is to argue that there exists at least a class of models in these asymmetric orbifolds where the moduli spaces are classically exact, so the metric receives no quantum corrections. Right, so of course there is a huge literature on orbifolds, and one can construct different types of orbifolds, but for today I will focus on orbifolds with target spaces of the following form. So we have a 5-dimensional Minkowski space times a circle and times a 4 torus. And this will be identified under the action of a discrete ZP symmetry, which we take to be an element of the T-duality group of the 4 torus. And here ZP is a cyclic group of order P. Now, specifically, the orbifold acts by rotations along the 4 torus, and these rotations are accompanied by a shift on the remaining circle. And here I denote the two complex torus coordinates by W1 and W2, and also I split in left and right movers. And now if we parameterize the rotations with 4 parameters, which I call here M1 up to M4, then the definition of the orbifold action is basically given in equation 2, where you can see that the left movers are rotated by the parameters M1 and M3, and the right movers are rotated by M2 and M4. Now, the nice thing about this parameterization is that for each of the parameters that is non-zero, then exactly 8 supersymmetries are broken. So if we want a model that preserves 8 supersymmetries, we have to turn on 3 of these parameters, and say we turn on M1, M2, and M3, and then M4 is 0, you can see from equation 2 that the left movers will always be rotated differently compared to the right movers. And so for this class of orbifolds, models with 8 supercharges are necessarily asymmetric orbifolds. Now about the shift on the circle. The circle coordinate is denoted by z, and then the shift is simply z goes to z plus 2 pi r over p, and r is the radius of the circle, and p is the orbifold rank, so it's the order of the ZP group. And now the shift is exactly what makes the orbifold freely acting, because by definition, the freely acting orbifold is an orbifold with no fixed points, and indeed, under the shift, there are no points left invariant under the orbifold action. Now, another thing about the shift, in general, the string states in the freely acting orbifolds, instead of being projected out of the spectrum, as it happens in the non-freely acting orbifolds, these states become massive. And also in general, the states that come from the twisted sectors are massive. And this is because due to the shift, the windings in the twisted sectors become fractional, and so these are non-zero, and non-zero windings contribute to the mass of the state. Now, let me explain a bit the spectrum of these models that we construct. For all the models that I consider here, the massless spectrum will contain always the gravity multiplet and 2 vector multiplets. And also here for this talk, I will focus on models with no massless hypermultiplets. And there is a condition on these parameters that we turn on, so it's condition 4. Now this says that no combination of these parameters should add up to 0. And if this condition is satisfied, then there are no massless hypermultiplets. And also, I will focus on examples with no massless Ramon fields, and I will explain in the next slide why this is convenient. And then similarly, there are 2 conditions on these parameters. So this is that the combination of M1 with M2 and M3 with M2 should not be 0. Now, if there are no Ramon fields, and in particular no massless Ramon fields, then the computation of the moduli space is a bit easier. And this is because if you first think of type 2 string compactified on a 5 torus and neglect the Ramon scalars, then there are only 26 scalars that come from the NS-NS sector. One of these is the dilaton, which parameterizes, in terms of the string coupling, the positive real line, this R plus factor, and the rest, 25 scalars, are the moduli of the 5 torus, and this parameterizes the coset S of 5 over S of 5 times S of 5. And of course, S of 5 is the T-duality group associated with the 5 torus. And now, in all the orbifolds that we construct, the dilaton is invariant under the orbifold action. So in the orbifold moduli space, this R plus factor will always be present. But the rest of the scalars that are associated with the 5 torus will not be in general invariant under the orbifold action. And so some of these will become massive, and they will not be moduli of the orbifolded theory. And this means that this coset space will be reduced to a subspace. And in order to find this subspace, we have to compute the subgroup of the T-duality group that commutes with the orbifold action. And this group I denote here by H. And this group will also be the T-duality group of the effective theory. I will explain later what happens in the quantum theory. And then if we also compute the compact subgroup, so the intersection of H with S of 5 times S of 5, then we have the moduli space of the orbifold, which is given by R plus times H over H bar. And the second thing about the absence of Ramon fields is that if there are no massless Ramon gauge fields, then in the spectrum there can be no BPS d-branes, and so we don't have to worry about possible d-brane instant-on corrections to the moduli space. So this was a brief review of the freely acting orbifolds. And now let me move on to the construction of dual pairs of orbifolds. And this discussion is based on a work by Sen and Vafa. And the starting point is type 2 string theory, compactified on a 4 torus with U duality group spin 5, and T duality group spin 4 over the integers, and with moduli space given by the coset spin 5 over spin 5 times spin 5. Now the idea to construct the dual pairs is that first we take two elements, G and G prime, which are in the T duality group of the 4 torus, and which are conjugate in the U duality group, but not in the T duality group. So this is the first line of equation 8 here. And the particular element H of the U duality group that we use for this conjugation is a combination of the S duality element S, which inverts the 10-dimensional axiodiladon, and the T duality elements T67 and T89, which invert the Kähler modulus of the 6-7 and 8-9 plane associated with the 4 torus. Now, if we take a point x in the moduli space that is invariant under the action of G, then the point h times x will be invariant under the action of G prime, as follows from this conjugation. And then, to construct these dual pairs, we further compactify on a circle, and we can orbifold at the point x by the action of G, and combine also with a shift on the circle, and we can orbifold at x prime by the action of G prime, and again combine with a shift on the circle. And then the orbifolds that I denote here by O and O prime are equivalent non-perturbatively, since the conjugation is inside the non-perturbative U duality group. And I will come back also with the exact dictionary between these orbifolds. Now, to give explicit examples of these models, we start here with a type 2b orbifold, which I denote by O, with the parameters, which is characterized by the parameters given in equation 9. And you can check that these parameters satisfy all the previous conditions that I showed for no massless hypers and no massless Ramon-Ramon fields. So this orbifold, its massless spectrum consists only of the gravity multiplet and two vector multiplets. And we can also compute the commutant with the T-duality group, which is in this case is given by SO11. And then the moduli space is simply R plus times R plus. So the one factor is parameterized by the 5-dimensional string coupling, it's lambda 5, and the other factor is parameterized by the radius of the circle. So these are the only two moduli for this model. Now we can use the dual pairs and construct a dual orbifold, O prime. And in this case, the mass parameters, these parameters are given in equation 11. And again, they satisfy all the conditions for no hypers and no Ramon-Ramon fields. And this orbifold again has in the massless spectrum only the gravity multiplet and two vector multiplets and the same moduli space, which we also expected from the duality. Now we take one step further and we construct the T-dual orbifold by performing a T-duality. R prime goes to 1 over R tilde. And here this orbifold, this T-dual type 2a orbifold, I know by this O tilde. And again, this orbifold has only gravity and two vector multiplets in the massless spectrum and the same moduli space. But now the important thing to keep from this discussion of the orbifolds and the dualities is that the initial orbifold, the orbifold O, and the final orbifold, this O tilde orbifold, these are related in a non-perturbative way. And the exact dictionary I write here in equation 14. And you can see, for example, if we take the strong coupling limit of the orbifold O at fixed radius, so lambda 5 is large and R is fixed, then the dual orbifold, the type 2a orbifold, is described by is weakly coupled and at large radius. and this is exactly the supergravity approximation. So in this regime, the supergravity approximation is valid, and so this is a classical regime for the dual orbifold. And I will come back to this in a moment, but for now, let me make some more comments on the moduli spaces of these orbifolds. And in general, the vector multiplet moduli space for theories with 8 supercharges in 5 dimensions can be described in terms of real spatial geometry by a cubic polynomial C of H, which is given by these DABC symbols. This is some numbers, and these scalars HA, BC, which should satisfy the condition that DABC, HA, HB, is equal to 1. And the indices ABC run from 1 up to the number of vector multiplets plus 1. And if you have these symbols, these DABC symbols, then we can also easily determine the metric on the moduli space. And also another thing that's important about these symbols is that these also determine the Chern-Simons couplings as they appear in the Lagrangian in the form of equation 16. And this is also important for the next. Now, to give one explicit example for the orbifold O that I presented earlier with moduli space R plus times R plus, this moduli space can be described by the cubic polynomial of equation 18, so it's 3h1 times h2 squared minus h3 squared. And in terms of these DABC symbols, this means that the only non-vanishing these symbols are D122, which is equal to minus D133 equals to 1. And so this, I say classical, these symbols, because all this story is valid at the classical level. But when we go to the quantum level, there might be some loop corrections to these Chern-Simons terms. And then if there are corrections to these terms, this means that these symbols will change in the quantum theory. So there will be different these symbols. But then if these symbols change, this means also that the metric will change at the quantum level. And this is a quantum correction on the metric. But now I will argue that this does not happen for the model O that I presented. And the idea is to first parameterize all possible quantum corrections that can appear, or in other words, to parameterize all possible deformation of this cubic polynomial. Now, the first term that we can add is a term proportional to h1, h2, and h3, but this is simply a field redefinition, and this describes the same space as the classical term, so this is not a quantum correction. Then the second option is to add terms that are odd in H2, H3, or combinations of H2 and H3, but all these terms are not allowed by the symmetries of the model. And let me explain this a bit more. Now, for this model, the orbifold O, the T-duality group of the effective theory was SO11, was given by this commutant H. And now the quantum level, this group will be broken to a discrete subgroup. In this case, it's just the Z2 group, which is exactly the T-duality group associated by the circle on which we perform the shift. And this group acts by inverting, by sending H2 and H3 to minus H2 and H3. So all these terms, which are odd in H2 and H3, or combinations of the two, are not invariant under this symmetry, so these terms are not allowed by this T-duality symmetry. So the only possibility left is to add a term that's proportional to H1 cubed. And this term is, in principle, allowed. So up to this point, I argued that for the type 2B model O, this orbifold, the only possible deformation of this cubic polynomial is the addition of a term proportional to H1 cubed. Now, we can go to the strong coupling limit of this orbifold. And in this limit, if we take the coupling very large at fixed radius, this term, which is proportional to H1 cubed, should dominate, as this is a quantum correction with respect to the first term, the classical term. But at this regime, we also have a dual description, which is given in terms of this type 2a orbifold, this O tilde orbifold, which now is weakly coupled at large radius. And now, if there exists a term proportional to h1 cubed, this would mean that the moduli space of the orbifold O tilde at the classical level would be described by exactly this term, h1 cubed. But this is ruled out because we explicitly computed the moduli space of this orbifold O tilde, and we found it to be R plus times R plus, and this space is not described by h1 cubed. So based on this duality, we conclude that D111 must be 0. And so since this was the only possibility, the only deformation of the cubic polynomial, and this is 0, then the cubic polynomial in the quantum theory is the same as in the classical theory. This means that there are no corrections to the metric on the moduli space. Okay, so I think the main message to take from this talk is that I gave you an explicit example of a model that preserves 8 supercharges in 5 dimensions with a classically exact moduli space. And the idea to prove this was first to parameterize all possible quantum corrections, all possible deformations of the cubic polynomial. Then we used the duality group of the model to exclude some of these terms, and for the remaining terms we used the dual pairs. And of course, this can be generalized to models with more vector multiplets or even to models with hypermultiplets. And today I just I just presented one example, but in the paper we treated many more examples. And finally, one natural thing to consider is to compactify these theories on a circle and see what happens there. So for the model that I presented with 2 vector multiplets, upon compactification on a circle, we get one more vector multiplet, and we have 3 complex scalars, which are usually denoted by STU. So this is an STU-like model. And now, in 4 dimensions, the vector multiplet moduli space will be described by the potential. And for this case, we can show that the prepotential cannot be corrected by any polynomial terms, but there can be exponential terms in ST and U that correct the prepotential. And so these are basically instanton corrections. But the nice thing that we also show is that if we take the limit back to 5 dimensions, all these instantons disappear. And so this verifies that indeed the 5-dimensional model admits no quantum corrections. Thank you.
Thank you very much, George, for the very nice talk. So now we could have some questions for George. If there is any question, please feel free to open up your mic and speak up. All right.
Yeah, I have a small question.
Yes, please, Maria.
Yes, from the beginning, very basic. Can there be additional massless states for particular values of the radius of the circle that you put additional circle?
Yes, that's possible. So for special values of the radius, this is usually at the same order as the string length. It's possible to obtain massless fields. But in this case, for the models that I saw, the models I presented, this will be a massless hypermultiplets. So in this case, this will not affect the vector multiplet moduli space. So, but yes, indeed, there can be massless states.
Okay, thanks.
Any more questions? All right. If not, maybe we can thank already at this point both George and Hamza for the very nice talks today.
Thank you.
And I guess we can stop the recording. So in case people want to ask something in a bit more informal manner, feel free to do so. We'll keep the meeting open for a little bit more. Otherwise, that's all from us from now. Thank you very much, everyone, for joining. Thank you very much to the speakers for giving these very nice talks. And we'll see you in 2 weeks with talks by Gabriela Casagrande and Jesus Huertas. Thank you and bye.